This video is for physics. Hello, good morning guys. And we're going to do a sample conservation mechanical energy problem so that you'll be able to do the problems that are due tomorrow by the end of the day. All right. Okay, so let's start. Oh, and all of this stuff will be in OneNote. So if you need to look at this, you don't have to go back to the video. You can take a look at the OneNote, but you do need to watch the entire video so that you can understand what's going on here, because these problems won't be exactly like my sample. And I'll have some hints for your number 27, because that's ask something a little bit different than what we're going to be doing right now. The equations. So mechanical energy is made up of kinetic energy and potential energy. And that kinetic energy has to do with the object moving. So in our problems, if we're like, hey, it's moving, it has kinetic energy. If it's not moving, its kinetic energy will be zero, and we'll use that to substitute in for our equation. For potential energy, we're talking about specifically their gravitational potential energy in this case. So that means if we have a height that's not zero, we'll have some potential energy. If our height is zero, we'll put in a zero for potential energy. And in problems 17, 15, yeah, you got two of those. Okay, so in 17 and 15, you may assume that mechanical energy stays the same because it's going to be like a smooth hill. There's no collisions. There's nobody pushing on anybody. So you may assume that the mechanical energy in 17 and 15 stays the same. And you should do them in that order. Okay, I think 17 starts you off a little bit easier. Okay. All right, so let's go ahead and do a sample problem here. So the words might say something like line rider or skier is released from rest on top of a 10-meter hill. All right, so there's my skier or my line rider at the top of the 10-meter hill. And maybe I want to know how fast he's going at the bottom of that hill. Maybe I want to know that velocity right there. And maybe I want to know how fast he's going at the top of the next hill, which is 3 meters. So maybe I want to know how fast is he going at the bottom of the hill and how fast at the top of the next hill. And I did say that line rider is released from rest. So this velocity right here will be 0 meters per second. And so what do you do when you get words like that? Okay, you draw a picture. You label your h equals 0, which I'm doing right now. Just like we did in the line rider activity, label your h equals 0. And despite it looking a little bit off, my height equals 0 is the lowest point in the problem that I care about, which is the bottom of this hill. All right, and now I'm going to pick spots. I'm going to number them. I'm going to call this spot 1. I'm going to call this spot 2, and this spot 3. So I'll go and put a V1 there, put a V2 there, V3 there. Okay, just keeping things straight. You can use A, B, C if you prefer. I'm going to use point 1, point 2, and point 3. And we're going to apply conservation mechanical energy. So similar to our conservation momentum problems, except easier because we don't have to worry about directions because these are scalars. Energy is a scalar, not a vector. So we don't have to worry about signs. I'm going to say the ME at one spot equals the ME at another spot. Okay? And it can be any of the spots on this problem because ME stays the same. So if I'm trying to figure out how fast it's going at the bottom of the hill, and I know some information at the top of the hill, I'm going to write ME at 1 equals ME at 2. So mechanical energy at 1 equals mechanical energy at 2. You do need to write that line. Otherwise, you'd have to write the whole, I'm about to apply conservation mechanical energy at point 1, point 2, yada, yada, yada. Just write that. It's so much faster. So ME at 1 equals ME at 2. Now, this next line that I'm going to write on this is optional, but I encourage you to do it because this is, if you do this next line and ask yourself some simple questions, you won't make mistakes. Or you're much less likely to make mistakes on these problems. So I'm going to expand ME out into KE and PE. I'm not even thinking yet. I'm just like, oh, ME is made up of KE and PE, so just write it. And after I write that, now we can do some thinking, and we can simplify right at this line right here. So ask yourself, is he moving? So at point 1, is he moving? No, because I said he was released from rest. Okay? So I'm going to go ahead, put that as 0. Just put a slash through at 0 because I don't have to worry about it. At point 1, does he have a height? Yes, he does. Okay, he has a height, so I'm going to leave that alone. Now I'm going to look at point 2, at the bottom of a hill. And this is a frictionless hill, by the way. Okay, we're assuming no air resistance, no friction. So if you go sledding down a hill and there was no friction at all, at the bottom of that hill, you're going to be going really fast. You're going to have a lot of kinetic energy because you're going to be going very fast. Remember that, I'm going to add this stuff now up here, that Ke equals 1/2 mv squared, and that gravitational potential energy equals mgh. So we're going to have a big speed, so we have lots of Ke, so not 0. But what about our height? At the bottom of this hill, well, I defined that to be a height of 0. So thinking about this equation, if my height is 0, my potential energy will also be 0. So no height or a height of 0, do that. Now I'm going to use these two equations and substitute in. Okay, if you want those a little bit neater than the previous PowerPoint as well, or previous OneNote as well. So I'm going to go ahead and plug in mgh1 equals 1/2 mv2 squared. And you may have realized this before we even started to do the problem. You're like, oh, it's all potential. It's going to be all kinetic at the bottom. That's great. This is the work to back it up to keep you from having to write an entire paragraph about what's going on. Okay. Also, it won't always be quite this straightforward. I'm going to be honest, it's not going to get much tougher than this. But this is the process that you need to be practicing. So I do need to see at least this line and this line. I encourage you to write that line to avoid making mistakes. Okay. And now, of course, the masses cancel out. So the mass of the object doesn't matter. Okay. It doesn't matter what the mass is if we're trying to figure out how fast he's going. If I said, what's the kinetic energy of the object at the bottom of the hill, you would absolutely need to know the mass because you'd have to find the speed doing this and then do, 1/2 mv squared, or you'd have to find the potential energy and say it becomes all kinetic. But you would need to know the mass if we were trying to find the actual amount of energy. But we're not. We're just trying to figure out how fast he goes, and the mass cancels out. Also notice, I did not tell you the angle of the hill. That was not information that was given or needed. That's the nice thing about these energy problems. They're not vectors, so we don't care about directions or angles, which makes the math that's involved significantly more straightforward than some of the other stuff we've done in the course. Okay, this can't solve everything. It's just another tool in our toolbox to help solve various problems and think about the world and model what happens in the world to figure out what's going to happen next or what happened in the past. Okay, so now we'll go ahead and plug in our numbers. Now this is the first time we're plugging in numbers to one of these problems, so I do want to emphasize that as long as you call the lowest point in your problem a height of 0, everything up here in terms of individual energies will be positive. That means this G is just the 9.8 meters per second squared. It's not the negative thing. Okay, so I'm just plugging in a positive 9.8 meters per second squared times my height 1, which is 10 meters, equals 1/2 v2 squared. Putting in the numbers there with units. 13 meters per second is how fast he's going at the bottom of the hill. That was it for that first part. Now let's figure out how fast he's going at the next hill, which is 3 meters high. Two ways to do this. One, you could redraw the picture and define this as a height of 0 and do the same process again, except ME at 1 equals ME at 3. Or you can leave the original picture and do ME at 1 or 2 equals ME at 3. Most people will leave the original picture and do ME at 1 equals ME at 3. So that's what I'm going to do. ME at 1 equals ME at 3. But you could also do, ME at 2 equals ME at 3 because mechanical energy is staying the same. Now, if you did ME at 2 equals ME at 3, you'd have to make sure you got this number right. Otherwise, it could mess up your next answer. Typically, this is what people do when we have if we were going to have a test, a traditional test, this is how I would recommend that you would do it to avoid extra mistakes. All right, I'm still going to expand this out for the sake of practice. So KE1 plus PE1 equals KE3 plus PE3. And then this is the moment where you stop and take a second and ask yourself some questions. Is he moving at location 1? No. So that'll be 0. Does he have a height? Yep. Now what about at location 3? Is he going to be moving? Remember, this is a frictionless hill. So even though you're released from rest at the top of a 10-meter hill, you're now cresting a smaller hill. So as you crest that smaller hill, you're going to be moving. You're going to make it over that 3-meter hill and be moving at the highest spot on that hill. So we're definitely going to be moving. Okay, not as fast as we were moving here, but we are going to be moving. And we'll have a height. So we have both of these things. We go ahead now and substitute in. So mgh1 equals 1/2 mv3 squared plus mgh3. Just using these equations up here. to plug in for each one of those, and putting ones were appropriate, threes were appropriate. And now M is in every single term, so I can cancel it out because M is in all three of those. If it was only in two of those, no luck, but it's in all three. Now I can plug in my numbers. So we'll have 9.8 meters per second squared times 10 meters equals 1/2 V3 squared plus 9.8 meters per second squared times 3 meters. And if you do it any of those other ways that I mentioned, you will get the exact same answer. No matter how you do this, you'll get the same answer. Also, you notice I didn't say which way was positive on this problem. That's because it doesn't matter, because this is just an energy-based problem. It does not matter which way positive is. All right, so 9.8 times 10. I really did that on my calculator again. In fact, I can just do 9.8 times 7. So let's just do the 9.8 times 7. And I'm going to subtract this from both sides. And then double that, and then square root. Basically, I'm just doing the algebra here. And we get 11.7-ish approximately. So 11.7 meters per second. There we go. Not quite as fast as we were going here, but still pretty fast. Still pretty fast. That's moving pretty good. But again, for no friction, no air resistance in this problem. All right. If you have questions on this, absolutely email me. I have additional resources that I can provide to you if you're having trouble following what's going on here. Also, remember, you can watch the video again. You can slow me down. You can click on the options and slow down the video to half speed or whatever, or pause it when you need to stop and think about what I just said, or listen to it again. And now the hint for number 27. All right. So this is specific to number 27. This should really help with 17 and 15 in chapter 11. Number 27 is a little bit different. If I remember correctly, it's a girl going down a slide. So she's going to go from the top of the slide to the bottom of the slide. And if you've ever gone down a slide, your backside warms up. Okay, even if it's a shade, even if it's in the shade or it's a cloudy day, when you go down a slide, your backside warms up. Okay, mechanical energy does not stay the same. That fact that you're feeling your backside warming up means that mechanical energy of the system has, because the surroundings, stuff's changing. The type of energy called internal energy is going up. That means the mechanical energy of the system, the girl here, needs to go down. But this question says, how much energy is lost? I'm going to phrase that a little bit, and I'm going to say, find the change in mechanical energy from point 1 to point 2. Okay, so this is her at the bottom of the slide. It's the worst drawing ever. It's still awful. But here's the girl at the bottom of the slide. Here's the girl at the top of the slide. Find the change in mechanical energy. And that will tell you how much energy was, in quotes, lost. If you do this correctly, if you do the delta correctly, and you take the final minus the initial, you should get a negative. Okay? But when the book says lost, I keep adding air quotes because energy is not lost. When one type of energy goes down for the universe, some other type of energy has to go up. We just haven't formally learned about where it's going yet, okay, where the other type of energy is going up at, okay? And to do a delta, I'll remind you that it's final minus initial. So what I would do is, if I were you to keep this as easy as possible, I would just find what is the ME at 2, okay? So it's like you're doing just like 1/2 of this. Like forget that this is here. Just figure out the ME at location 2. Add up the KE and PE and get a number. Then find the ME and the KE and add it up for location 1. Then do your delta. Okay, and like I said, you should get a negative. I don't know what it'll be in the key. It'll probably say a certain number of joules lost. You should get a negative when you do that. And remember, G is still just a positive 9.8. Now you might be saying, Mr. Willard, you just said that energies are always going to be positive. Yes, they are. Okay, the number you get here will be a positive number. The number you will get here will be a positive number. The key is the change in that number can be negative. And I'll give you a comparison to your weight. You talk about stepping on a scale. If you weigh one day 150 pounds, okay, and then the next day you weigh 145 pounds, both of those numbers were positive, 150 and 145 pounds. If I said, what is your change in weight, you would tell me minus 5 pounds. Okay, you would tell me minus 5 pounds. You lost 5, you in quotes, lost 5 pounds. You went from 150 to 145, because you would take the 145 minus the 150 and you would get a negative 5. It doesn't mean your weight was ever negative. It just means that that amount of something went down. So when you're finding changes in things that are scalars, okay, like energy, If the delta ends up being negative, it means the quantity went down. If the delta ends up being positive, it means the quantity went up, whatever that thing might be. So hopefully that helps there a little bit with the math. Don't sweat that too much. If you get a positive answer, but it's the right size, I'm okay with that. You can just put that many joules lost, and that's okay for what we're doing right now. Okay. Good luck, guys.